Good morning, and my name is Nathaniel Mendes, and my group is with Ryan Livingston, Avery Johnson, and Brandon Blunt. We are in Physics 2513. We are going to be talking about, our main topic will be energy, the subtopics will be friction, spring, conservation of energy, work, and momentum. We're going to be working 3 in the take-home quiz.
A 10-kilogram block is released from point A in the figure. The track is frictionless except for the portion between point B and point C, which has a length of 6 meters. The block travels down the track, hits a spring force constant of 2,250 newtons per meter, and compresses the spring 0.3 meters from its equilibrium position before coming to rest momentarily. Determine the coefficient of kinetic friction between the block and the rough surface between B and C. So, we know that this problem gave us our M, which was 10 kilograms. It also gave us our height, which was 3 meters. It also gave us our spring compression value of 0.3 meters. They gave us our distance between both of these points B and C, where the friction is located, which is also equal to 6 meters. Correctly notate that, all right. Put 10 right here. And they also gave us our spring constant, which is 2,250 newtons per meter. All right. Though it seems like it's a lot going on in this problem, you can really break it down into 2 phases. This would be your phase run before it gets to points B and C, where the friction is occurring. And phase 2 would be when it passes that friction and when it hits that spring constant. And we can approach this using the summation of all energy in the initial phase is equal to the summation of all energy in the final phase, which is otherwise known as the conservation of energy.
Hi, I'm Brandon. I'm going to take over for Ryan here. So we have the conservation of energy here, and since Ryan said this half, the initial part, would be this side, essentially this side is one part of it, is just this part, and this side is just this part. So on this side, we need to have the potential energy, because it's just sitting here. The work due to friction initially, because we're gonna have friction on this side, because that's what we're looking for. And we need to have the kinetic energy on this side, on the initial side. This will be 0 because there's no kinetic energy being worked on here. This will also be 0 because it's just sitting there. There's the same concept as here. These will both be 0. So on this side, we have the final of the energy, otherwise known as this side. On this side, for the final, we need to find the work done by friction, because of this, plus the potential energy of the spring, because the weight, the mass, hits the spring. And we need to find the kinetic energy of this side. Now the kinetic energy will be 0, the final kinetic energy will be 0, because it ends in rest. So now we're going to plug in our equations for each of these values. The potential energy for the top part, for this half of the equation, is mass times gravity times the height. Because this side, the work due to friction, is mu k, which we're looking for, times n. And if you remember, work is force times distance. This is the kinetic force, work due to friction, the work due to friction, and then times our distance, plus the equation for the potential energy of spring is 1/2 kx squared. Now, we need to find this, our mu k value. To do this, we move 1/2 kx squared over to this side, which will give us mgh minus 1/2 kx squared equals mu k times the normal force d. And to find mu k, we just divide by the normal force and the distance. And there we have our mu k value. So from here, we need to find the normal force. And the way we're gonna get the normal force is mass times gravity. We can write that down here. Normal force equals mass times gravity, since there's nothing else acting on it in the X or Y direction, or in the Y direction. There's something pulling up on it. So all we have to do now is just rewrite the equation as mgh minus 1/2 kx squared over mg times the distance. And that will give us our UK value.
All right, and I'll take over for Brandon. All we have to do now is plug in our values and we'll get our coefficient of kinetic friction. So we know that the mass of the block that was dropped was 10 kilograms. We also know that acceleration due to gravity is equal to 9.8 meters per second squared. And that's translational. And we also know that the height from which the block was dropped from is equal to 3 meters. Now we just plug in our spring constant, which was 2,250 newtons per meter, and our x, which was 0.3 squared, and all that over mgd, which is again 10 kilograms multiplied by 9.8 meters per second squared. But this time we're multiplying it by the distance between points B and point C so we can find our kinetic friction coefficient. Okay, from here we can basically tell that this is equivalent to Newton, and this basically cancels out all of these, and your mass is canceled out right here as well as your acceleration right here. This also canceled out, so you're left with nothing but a value of the coefficient, which is equal to 3.328. All right, we can actually take it back and do a quick little recap. In the scenario, we were given a block that was dropped at point A, slid across a frictionless surface, and reached a frictional surface at points B and C with a displacement of 6 meters, where it then crossed and hit a spring, where it compressed it to 0.3 meters, and it bounced back, reaching its point of rest. And for this, we can use our conservation of energy equation, which is equal to the summation of all energy in the initial phase is equal to the summation of all energy in the final phase. And we would use our potential energy, our work of frictional force, and our kinetic energy in the initial phase, making it equal to the work of the frictional force in the final phase, the potential energy in the final phase, as well as the kinetic energy in the final phase. Okay, we know our potential energy in the initial phase is equal to mgh. However, since both of these are equal to 0, they're not going to be on the left side. So we go on to the right side where we find the work for our frictional force, and we know that mu k, which is our coefficient of static friction, times the force times distance is equal to our work of frictional force overall. And we have our potential energy in the spring, since our spring was both compressed and it exerted a force on the box to bring it to rest. And we know that's equal to 1/2 kx squared. All right, from here we can just move everything around algebraically. We'll subtract our potential energy in the spring and move it to the other side, and then we'll divide by the force of the friction and the distance where it traveled between points B and point C to find our coefficient of kinetic friction up here. From there, you can just plug in your numbers and you'll be left with 0.328. And you'll know that it's a coefficient because you won't have any units at the end.